So yeah, let's get started now. Welcome everyone to this week NL seminar. Today we are very excited to have Jonas Pfeiffer as our guest speaker. Jonas is a research scientist at Google Research. He is interested in modular representation learning in multitask, multilingual, and multimodal contexts, and in low-resource scenarios. He works on his PhD at the Technical University of Darmstadt, was a visiting researcher at the New York University and a research scientist intern at Meta Research. Jonas has received the IBM PhD Research Fellowship Award for 2021-2022. He has given numerous invited talks at academia, industry, and ML summer schools, and has co-organized multiple workshops on multilinguality and multimodality. He is also one of the main contributors of Adapter Hub. Today, he will give a presentation about his research on modular and composable transfer learning. As a reminder, there will be a Q&A session at the end of the talk if we still have room for that, but feel free to ask any questions anytime you might have something throughout the talk. And to ensure the clarity of the talk, please continue to mute your mics unless if you have a question or a comment. Thank you again, Jonas, for accepting our invitation despite the time difference with Europe, and I hope you enjoyed this talk. And with that, I hand it over to Jonas to get started.
Yeah, thank you so much for the invitation. Yeah, I'm really glad to talk about some of my work and also the work of many other very cool people, and hope to get you more excited in modular transfer learning. So I will start my talk with explaining on a very high level what I mean by modularity and compositionality. I'll give a brief introduction to what adapters are and how and link adapters to modularity. I will then provide you with an example for out-of-distribution generalization capabilities of these modular components, specifically in the example of cross-lingual transfer. And finally, I will also provide more details about how we can mitigate catastrophic interference during pre-training by modularizing models at the get-go. So what do I understand under modularity? So let's assume that we've learned a task or a skill in one modular black box and another skill or task in another black box, and we would like to compose these two modular components in a way such that they perform better in an unseen scenario, for example, on a third task. So why is this interesting? As we all know, models are increasing in size, and there's just a dire need for us to design parameter-efficient fine-tuning strategies. Secondly, there's a lot of unseen scenarios, meaning, for example, that we again have a skill and maybe only training data in one high-resource language, but we would like to use this this training data and this scenario for an unseen language. So we'd like to compose these modular building blocks such that we can generalize well in new scenarios, for example, in cross-lingual transfer, especially in low-resource languages where we often just don't have any training data available. Also, there's a lot of catastrophic interference when we try to train a model on many different modalities, such as images, videos, speech, text in different languages. These modalities tend to interfere with each other, and maybe by integrating modularity from the start, we can mitigate this this interference. And finally, models are basically outdated the minute that we stop training, also with respect to us always having an updated data set. But these models quickly are outdated. And instead of us actually fine-tuning the model again on every single on the data that comes in daily, maybe by integrating a modular update that is more parameter efficient, we can only integrate the new information instead of it requiring us to pre-train the model from scratch again. Okay, so in normal fine-tuning, when we start with a pre-trained model, for example, BERT, T5, whatever model that we're interested in, we usually fine-tune all the weights on the target task. So that means we define our loss function, the models of the parameters of the model, and we optimize all the weights, the ones that that were already pre-trained on the unsupervised tasks such as MLM. For adapters, it's a bit different. We actually pull apart every single layer of the transformer and stitch in new weights. So when we define those weights as phi, we actually encapsulate these parameters phi between the pre-trained transformer weights theta. And encapsulate it because we now freeze the pre-trained weights and only fine-tune the newly introduced adapter weights on the target task. Okay, so the architecture that was first proposed is the bottleneck adapter, and that consists of a down projection, a nonlinear activation function, and an up projection, and it can be placed at different parts of the transformer architecture, depending on what modality we're working on. Different positions of these bottleneck adapters are important. So for example, in vision tasks, it tends to be more important to add this adapter after the multi-head attention layer, whereas for NLP tasks, that doesn't change a lot. It has to be placed after the feed-forward layer. So it's more of an empirical evaluation where these adapters have to be placed rather than, you know, some more profound reasoning, I guess. So what is the performance of these adapters? I mean, now we've added more capacity to the model. Does it perform better? So if we look at the tasks of the glue tasks, here we present the results for full model fine-tuning in red and the two versions of bottleneck adapters in blue. And we can see that the performance is somewhat the same. Yeah, just a reminder, we're not actually fine-tuning all the weights of the transformer, but only the small layers that we add to the that are randomly initialized, and the pre-trained weights are all frozen. And this boils down to the number of trainable parameters. While the performance across all tasks is somewhat the same, for full model fine-tuning, we fine-tune all the weights of the pre-trained model. For BERT, that is, for example, 500 megabytes, whereas adapters only require a very small amount of parameters that are updated. Putting that into perspective, if we fine-tune 2 tasks with full model fine-tuning, this accumulates to the same amount of parameters that more than 200 adapters require. So for the same amount of parameter space on your GPU, you can fit more than 200 adapters and 200 tasks on your GPU, and only 2 fully fine-tuned models. So this puts it a bit into perspective and demonstrate the effectiveness on a parameter efficient fine-tuning level, why adapters are quite interesting from that perspective. Okay, so this bottleneck adapter was one of the first ones, but this research direction has been very popular in recent times with prefix tuning, where they extend the key and value matrices at every single layer, and is basically a generalization of prompt tuning. Then there's the compactor, which actually reparametrizes the bottleneck adapter to be more parameter efficient. We have LoRa, which also reparametrizes the query and key matrices. There's parallel adapters where the representations are not processed sequentially like the bottleneck adapter, but instead, in parallel. There's UniPelt that actually is not really a new adapter architecture, but instead a gating mechanism that learns to identify which adapter is most useful for the respective target task. And finally, most recently, there's IA cubed, where that is extremely parameter efficient, as only a linear vector is multiplied element-wise with the representations within the multi-attention layer, but also in the up projection feed-forward layer. So all of these approaches are some sort of an adapter, and they have different objectives, what they're trying to solve. Most of them are interested in parameter efficiency and basically performing well on the target task while requiring very little amount of trainable parameters in the model. They have some benefits, some limitations, especially what we see in recent times is that for generation tasks, the models do need more trainable parameters, and that restricts some use cases or some adapters from being used for those scenarios. We'll have a more thorough investigation of that coming out in the next month or so. But basically, even though a lot of these models perform well on a set of tasks, that does not necessarily translate to all of them. And it turns out that giving the model a lot of capacity or a lot of trainable parameters is the most flexible, quite obviously the most flexible way. As we've seen, the bottleneck adapter also does not train that many parameters. But in general, what I will basically talk about in the rest of my paper should to some degree also translate to the other architectures that I have on the slide here. But in my talk, I will predominantly talk about the bottleneck adapter. I'm not sure if there was a question. Let me just check that. Okay, no. Yeah, if there's a question, I can't see the chat. So best case scenario, you just blurt it out and interrupt me and not write the chat for now. Okay, so so I will predominantly focus on the bottleneck adapter from here on out. So the question that we have is whether or not these adapters are in fact modular and composable. So that is the question. Are they somewhat interchangeable, even though that they are trained independently of each other? So basically, we can train multiple adapters on different tasks, and because of the surrounding parameters that are frozen, the question is if this freezing of the surrounding parameters results in adapters that are somewhat interchangeable. Okay, so on a higher level, what might happen if we define an arbitrary compositionality function? For example, if we say that we have 4 adapters trained on 4 different tasks, so we have one adapter trained on the yellow task, one adapter already trained on the purple task, and so on. And we define a compositionality function that tries to utilize the information from all these adapters to solve the same set of tasks again. What could happen is that this compositionality function could identify, well, okay, like this adapter was actually trained on my task, on my own objective, so I'll just select my own task adapter again. The other thing that could happen is that instead of selecting the respective own adapter, the model could, the compositionality function could identify one single adapter that performs very well for all the target tasks. So one example for that is MNLI. So multi-NLI is a very good task to train on in an intermediate step. And this task, this intermediate data set transfers very well to a set of target tasks. So this could also happen. There's one adapter that performs best on all tasks. And finally, what we would ideally like to see is that this compositionality function is able to combine the information of multiple adapters to perform well on a third adapter. And if that is the case, if the model is actually able to combine adapters from multiple different sources, basically, then that might indicate that even though we've trained these adapters independent of each other, they are to some degree modular and compositional. Okay, so let's take a closer look at one compositionality function that we've defined. So similar to my previous slide, let's take 3 adapters trained on different tasks. And now we will learn a attention mechanism, which takes as input, as the query input, the input to all the adapters. So this is the same representation passed into all of these adapters. And the output of each of the individual adapters is interpreted as the value in key. So the dot product of key and query followed by softmax weighting learns to dynamically weight the representations of all the respective adapters at every single layer. So it's the dynamic weighting on on the layer level where the model can, or the attention mechanism can ideally identify which adapter is most useful to solve the target task. And not only the single most useful, but actually a combination, a weighting of a set of most useful adapters.
It looks like, so the query is from the pre-adapter layer, as opposed to having like self-adapter attention. Is there a reason you might want to do, say, self-adapter attention, or we're just gonna kind of combine the 3, or does that not really? I guess that would only make sense if you were propagating the 3-way thing forward, right?
Sorry, I didn't fully get that. So this
I think I retract my question. So you're basically, it's kind of like you're saying cross attention between the pre-adapted element and the 3 adapted cases, right?
Yeah.
Okay, great. Thank you.
I have a question.
Mm-hmm.
The adapter fusion layer is like very, it has like much more parameters than any of the individual adapters, right? Like in my own experiments with adapter fusion, I've seen, like in my case, I had adapter layers that was like less than 2 million parameters, but then my adapter fusion was like 20 million or more. Because basically you have like an attention network here, and like the query key value matrices are like pretty large.
Yes. So the adapter fusion technically is quite large, given these 3 matrices. However, the key and query matrices just accumulate to a weighting. So while it is a large number of trainable parameters, the actual capacity of the key and query is quite limited, because it's just a weighting of the respective output representations. Technically, the value is the only matrix that has the capacity to transform the representations. However, we initialize it with a diagonal of 1s and very, very small weights on the non-diagonals. and regularize this value matrix such that it ideally is remains to be the diagonal of ones. Basically, you could, in an ideal scenario, what would also be possible is to replace the entire value matrix with just, not having it at all. And then it's a direct pass through of the representations of the adapters. And that does work to a certain degree, but we did learn that the value matrix does need, or the representations out of the adapter do need slight transformation. But yeah, like it is a lot of parameters, but we're trying to limit the actual capacity of the adapter fusions quite significantly so that it's a fair comparison in the end run. I think that if you're just interested in downstream task performance, you can also try to not regularize the value matrix at all. We did see that initializing it with a diagonal of ones is quite important. Otherwise, basically, the adapter fusion mechanism has to relearn everything, which, especially in few shot scenarios, often doesn't work at all. So that was one key ingredient, I would say. But yeah, the regularization aspect of it can be eliminated if you're just interested in downstream task performance. But yeah, in general, like if you've played around with adapter fusion, you've probably also realized that it's very slow. The more tasks or more adapters you throw in, it's very, very slow. That's definitely a downside. There are ways of mitigating that a bit by dropping adapters during training, but also during inference. So you can technically only sample a few adapters at every step, and then keep track for each task which adapter was activated. So that improves the speed a bit. But in general, I would say that this adapter fusion mechanism definitely is not the best way to compose representations of adapters. And unfortunately, there's not too much work that I know of that goes beyond adapter fusion, but I'm hoping for others to jump on that train and come up with better solutions than this very inefficient way of composing adapters.
Right. Yeah, thanks for the answer. And sorry, I have another question jumping off of something you mentioned. So you mentioned initializing the value matrix with a diagonal of ones and like zero-ish values elsewhere. Do you also is it also possible to do something to control the the distribution coming from the softmax so that it's initially concentrated on like the current task, so the model so the model initially learns initially gets representations from the adapter that it was originally trained on, and then learns to shift away from that, or
so
add in knowledge.
We'll see that in the next slide, that the model automatically learns that. But I would actually argue that this specific scenario is very academic in nature, because if you already have in more realistic scenarios, you wouldn't actually have a task adapter available, right? Or you would fine tune it together with the other adapters. It's the scenario that we designed here is academic in the sense that we're trying to identify whether or not the adapters are actually modular. And if you would try to use adapter fusion in order to perform better on the target task, you would not design it in this very restricted kind of way, and probably not even have an adapter already pre-trained, but do something else, because your end game in that sense is kind of perform well on the task that you're actually interested in. And why limit the model from learning more from that respective task?
Right. Yeah. Fair. Thanks. Thank you.
Yeah, so yeah, I jumped ahead a bit. So let me just go into detail about the experimental setup a bit. So we have 16 tasks that we trained adapters on. And then we learned this adapter fusion mechanism and try to perform well on the same set of tasks. And the reason why we're also fine-tuning on that respective task that was already in our pool of pre-trained adapters is precisely what I just mentioned, that we want to identify if an adapter will always just, or this fusion mechanism will always just select its own adapter, which would kind of, suggest that these adapters are not that modular. And so we can look at the activations of adapters. In this heat map here, we have the activations at different layers of the transformer, where on the y-axis, we have the target tasks that we're fine-tuning now. So this is the tasks that Fusion is trained on. On the y-axis, we have the adapter that was activated through Fusion at that respective layer. The diagonal indicates that the model or the fusion mechanism has identified that its own adapter is the most important one at this specific layer. So for example, here, MNLI at layer 1, selects its own adapter at that specific layer.
This is a per word decision also, right?
The adapter fusion is per word, which is also quite inefficient. I would nowadays argue for it to be on the sentence level or example level, but here it is averaged over the tokens at that layer, yes.
So wait, so you have a distribution over adapters over tokens. You're just plucking off the whatever the not softmax, but the incorporation percentage is for each one, and then just doing straight averaging across all instances of, say, layer 1 for all inputs at test time.
Yes.
Okay, great. It looks like it's quite sharp anyway.
Yeah. Yeah, so a lot of these tasks are pretty sharp. Sorry.
So for cases like RTE, which is like brightest at RTE but not very bright. And I mean it's pretty black outside of my end diagonal. Is that to say that this basically is just never really strong on any adapter?
Yeah, well, like it really depends on what layer we're looking on. So for example, RTE at layer 9 definitely selects MNLI, which makes a lot of sense because it's an NLI task. And actually,
y-axis is the task you're training on, or y-axis is the adapter you're inheriting from?
So y-axis is the task that we're training on, and X is the adapter that was selected at that layer.
Okay. So it's highest on multi-NLI. There's still orange. I don't know where orange goes in the ranking from white to black, but still it's never white anywhere.
Yeah, it is. Yeah, I mean, it might be the case that it is a bit, it's not as distinct at selecting one specific adapter, but again, like this is an averaging over all examples. I think of the test data set or the development data set. I guess we don't have test data available for dev for Glue. And across all tokens. So this very white activation here, is basically that the model is very, very sure that this is the only adapter that it needs to do. use, whereas for the other tasks, it might, for some examples, use another adapter at that respective layer.
So for the, I guess it's MRPC and CD, and also RTE, it's like never really sharp even for its own task. Is there some big, do you think there's some big difference in the way the adapter was built and the way it's being used in Glue, or is it just really like, it's just, I don't know, it seems very counterintuitive unless there was some weird disconnect.
Yeah, so if we actually look at the results, then we can see, so what we have here is the relative performance gains of adapter fusion over just fine-tuning the adapter itself. And we sort, so basically 0 means fusion does not give any performance gains at all, whereas higher numbers indicate that fusion actually helped perform better on the respective task. And if we sort the tasks by from high to low resource, then we can identify that especially the low resource tasks profit from the adapters trained on different tasks, whereas the high resource tasks don't tend to perform better or perform more or less the same. And this is actually precisely what we can see here. The lower resource tasks activate different adapters, and instead of using their own adapter, so they're able to basically utilize the information stored in other task adapters to perform better on their own task. And CB is an example where I think we only have 250 training examples available. And so the model or these adapters are probably just not able to learn anything that meaningful, and instead are better at using like MNLI, which is closely related to that task.
Are you going to talk about what happened with Grande?
Yeah, we don't know. Really, like that's one of the questions that I always get. I tried to look into it. I heavily tweaked it. I never got it to work better. Like, it might be that there's just a distribution shift between train and test data. I really don't know.
You gotta have one, right? Otherwise it looks too suspicious. So anyway, it's good to have something.
Yeah, I really don't know what happens with Minor Grande. It was very annoying. Yeah. Okay. Cool. So as we've seen, for some tasks, the model or this fusion activation is able to combine representations of multiple adapters. Actually, I didn't actually talk about that. So I think one example here is quite interesting, that at layer 7, CB is able to combine multiple adapters at the same level, same layer. So yeah, like for others, I guess here, for example, the sentiment analysis data set at layer 1 is very distinctly using MNLI. And at layer 7, it, I guess, uses its own adapter. And yeah, I don't know if this is, yeah, here it uses IMDb data, for example. So it is able to combine the adapters of multiple different tasks at different layers. So we would argue that these adapters are modular and composable, at least to a certain degree, even though that we've trained them completely independent of each other. Cool. I'd go over to the cross-lingual transfer now, unless there are more questions about fusion. Okay, cool. So here we're looking at basically the idea is, now that we've established that adapters are modular to a certain degree, how can we utilize that concept? And we'll specifically look at the task of zero-shot transfer to low-resource languages. So the usual process is that we pre-train a model on massive amounts of text, monolingual text in different languages. We then fine-tune the model on a task in a high-resource source language and transfer and evaluate the model on a low-resource target language. And this is very important because training data is very expensive and often not even available for many of the languages that we're interested in, especially ones that we consider low resource. So ideally, we would like to have one model that is able to perform a task in any language that we input the data in. So as all of you know, there's a bunch of massively multilingual models such as MBERT and XLMR, and they achieve quite good results on a number of high-resource languages, but they suffer from the so-called curse of multilinguality, where the performance especially deteriorates for languages that are not covered during pre-training, and that makes it very difficult or basically impossible for us to represent all the 7,000 languages within a single model. In our approach, we still assume that due to this massive multilinguality of MBERT and XLMR, these models remain to be the perfect grounds to be transferred to unseen languages. And so we propose an adapter-based approach where we learn adapters for languages that were seen. So for example, English and Chinese, so MBERT, XLMR, they were all pre-trained on English and Chinese data. But we also train adapters on unseen languages, such as Quechua and Guarani. We also train task adapters, for example, on named entity recognition. And we try to basically stack these adapters and disentangle the language from task concepts so that we learn somewhat language agnostic task adapters, so that we can replace them during zero-shot transfer. And how we do that is going to be the topic of my next few slides. So MADX consists of multiple steps where we train a language adapter on the source and the target language, where we freeze the surrounding parameters, only fine-tuning the adapters on monolingual data of the source language, but also the target language. So now we have blue English adapters and green Quechua adapters. In step 2, we then train task adapters, and these are stacked on to the output of the language adapter. And because we want to replace the language adapter during inference, we freeze not only the pre-trained transformer weights, but also the language adapter, only fine-tuning the task adapter on the training data in the source language. So that in step 3, during zero-shot transfer, we replace the language adapter from English to our target language adapter while retaining the task adapter that was trained on English data. Cool. So we evaluate the setup on a number of source languages. So for example, English, Chinese, Japanese, Arabic, they all come from different language families and are written in different scripts. And we transfer to a set of seen languages. So these are languages that the model has been pre-trained on, but that are somewhat under-resourced during pre-training. We also transfer to a set of unseen languages. So those are languages that the model has not been pre-trained on, but uses script or are written in scripts that the model has seen before. So for example, Wolof is an African language that is written in Latin script. So the fallback option for the model is always basically character level tokenization. And finally, we transfer to a set of unseen scripts. So those are languages that the model has not seen before, but also the script is of that language is a script that the model has not been pre-trained on at all. We evaluate on a number of different tasks, but we're only going to go into detail about NER. So let's first of all look at MBERT. Here the performance, as we can see, drops significantly when we go from seen to unseen scripts. And when we look at MADX, we can see that there is a small performance gain for seen languages. We suspect that that is the case because, yeah, the script and the language is somewhat underrepresented in MBERT, but we see a large gain in performance for unseen languages. However, for unseen scripts, we can see that our approach is not able to actually perform well at all, where both MADX and MBERT basically fail. And why is that the case? So let's, for example, look at the Amharic script, which looks like this. Now, if we try to tokenize this specific script with the MBERT tokenizer, then the fallback option, even though MBERT has seen hundreds of languages in many different scripts, this specific script is not represented in the MBERT tokenizer. And so the fallback option for MBERT is basically still unknowns. So there's no way for the model to actually represent this sentence at all. So in our follow-up paper, we try to mitigate that. And the simplest approach is basically replacing the embeddings and MBERT tokenizer that was trained on, the MBERT languages with a new dedicated tokenizer that we train on unsupervised textual data, and randomly initialize the new corresponding embedding matrix. Now, the problem is that a large portion of the model parameters consists of the embedding matrix, and so we might lose a lot of information if we just randomly initialize this embedding matrix instead of trying to capture some of the information stored in the original embedding matrix. And in our paper, we try out many different things like a matrix factorization and clustering ideas, and they all help to a certain degree, but it turns out that the simplest approach, which is basically copying lexically overlapping tokens, for example, entities that are borrowed from different languages, but also numbers, performs the best and achieves almost on par with the approaches that we propose in the paper that are significantly more complicated. So that's why I would suggest anybody who tries something like this not to worry about these alternative approaches that we propose, but instead just lexically copy the embeddings from the old embedding matrix to the new one, and that performs very, very well already and is a lot simpler to implement than the other complicated methods that we propose. Okay, so now we have a Amharic tokenizer, and we have.
Can I ask some questions about the tokens?
Yep.
So, sorry, are the Amharic tokens? Those are random. You don't do any. You don't transfer from like. Yes. That's okay. And then, how are you determining the subword units?
So we have the original subwords from MBERT, and we don't have any special rule of how we construct the subwords. Actually, that would would probably not be stupid to look at some of the subwords that MBERT actually has already for the respective words. We did not do that. So you could probably even improve on that, because there will be some subwords that were tokenized and that technically exist in MBERT, but because the subword tokenizer of Amharic just did it slightly differently, it does not. That would probably be better.
So wait, so for Amharic, you're learning a new subword vocabulary from whatever Amharic data you have?
Yep.
Right, and then you're using that new vocabulary completely and only using the MBERT things that, but only starting with the Ember things that you happen to need to transfer in.
Yeah, so only the tokens that by chance also exist in the Ember tokenizer, those are copied into the new embedding matrix.
Okay, thank you. Oh, and also I was saying, the fact that you got anything that was non-zero in NER for those unseen scripts, that implies that you probably have entities that are just written in other scripts in that data, right?
Yeah.
What was
question.
Is this what's it called, Wikian?
The script name, I forgot.
No, the NER data set that you were evaluating on.
Oh yeah, Wikian. It's noisy.
Yeah,
it's Silver
not to
Standard.
throw
Yeah.
myself under the bus, but yeah, pretty noisy. Lots of Latin inheritance.
Yeah. It's not a good data set to evaluate on, but back then there were just no other data sets out there. Now there's a lot of data sets for African languages, like Masaka NER. There's also America's NLI that are definitely more interesting than Wikian. Back then, this was basically the only thing that we were able to evaluate on. There are, I think, follow-up works that try out these approaches also on those data sets, and the results are somewhat similar.
Thanks.
Yeah. Cool. So basically now we have a semi-random initialized embedding matrix, and we fine-tune those together with the adapters on, again, unsupervised data in the target language. So in MADX, we only fine-tuned these adapters. Now we also fine-tune this embedding matrix. And one assumption why, this initialization from the lexically overlapping tokens works better is maybe because it anchors the embeddings, but also probably especially words that are borrowed from different languages just have a bit of a better embedding representation from the original language. We did not investigate that further, but it's more of an assumption why this is so important and results in very large gains. I'm not going to go into detail of that. You can check out the paper, but it's quite significant. Okay, so now let's get back to that slide where we saw that both MADX and Ember completely fail for unseen scripts. Now, if we add this additional tokenizer, then we can see that the performance significantly improves for unseen scripts. So now we've basically adapted Ember to not only unseen languages, but also unseen scripts with pretty decent results. Cool. Now, due to time, I will not go into too much detail here. We basically do the same stuff for multilingual visual question answering. We provide a new data set where you answer questions in different languages, do it with adapters. Not that surprising or not that exciting, I would say. Check it out if you're interested in multilingual PQA. It's a very, very difficult task. Everything that we know of multilinguality and cross-lingual transfer does not really translate to multilingual, multimodal scenarios. So a lot of work to be done in that field. Check out the paper. We also have a IGLU benchmark on more data sets. Please work on this field. It's difficult. Okay, so the final part, and I'll rush over it a bit, is utilizing modularity to mitigate catastrophic interference during pre-training. So as I've mentioned earlier, these massive multilingual models, they all suffer from the curse of multilinguality. And we assumed in MADX that they are still the best grounds to be extended to more and more languages. But the question is whether or not that is true. So we ask ourselves if modularization can actually mitigate catastrophic interference, and if we modularize the model from the start, if it's actually easier to add new languages down the line. So a recap: in MADX, we started with a fully shared model and added adapters later. In this specific scenario, we add modules already during pre-training, and hopefully this creates a model that expects added modules later on down the line. So we compare a standard fully shared multilingual model with our modular approach. And in order for us to maintain the number of float point operations, our fully shared model actually has a single module or adapter that is shared by all languages. And the residual connection around this modular component lets the model decide whether or not it wants to use this additional module or not. So yeah, similar to MADX, we have one module that is used by each of the different languages, but now we train it from the start. So every language has the capacity to learn idiosyncratic information in the respective modular components in the modular version of the model. So in order for us to actually measure the curse of multilinguality, we have a problem, because during pre-training, if we train a model on more and more languages, so we train one model on only one language, another model on 2 languages, another model on 3 languages, and so on, we have to decide what data we train this on. And for example, if we fix the number of update steps, meaning that all models have to be trained for the same number of update steps, let's define it at 125K, then the first model is trained on English for 125,000 update steps. Now the second model is again trained for 125,000 update steps, but now the model sees less examples in English. And this problem gets worse and worse with the more languages that we add in. So the first model has seen a lot more examples in English than the last model that is now trained on 5 languages. Now, if we go the other way around, where we fix the number of examples per language, so let's say, again, the first model is trained for 125,000 update steps. Now we add French for the second language. Now we have to train for longer and longer. And both aspects might have an effect on the model, depending on, because either it's trained for shorter, but for every model has seen the same, is trained for the same number of update steps, or every model is trained longer, but the same number of examples are seen by each model. And we don't really know how to solve this, so we just try out both. So let's first of all look at the perplexity. And these are models that all have seen the same number of examples per language. So on the y-axis, we have perplexity. Each plot is a different language. Orange is the shared model. So all parameters are shared between all languages. And blue is the modular model. And again, perplexity is the higher the perplexity is, the worse the performance is per language. And we can see that for all languages, the curse of multilinguality or catastrophic interference between languages is actually kicking in, whereas the modular version does not suffer from that problem, where the performance, at least on perplexity level, is maintained. So we're not interested in perplexity, but actually transfer performance. And so similar to the MADX approach, we freeze the modular components, but now we don't add adapters, but actually just fine-tune all the weights that are shared between languages, so that during inference, we can again replace the source language with the target language module. So let's look at the downstream task performance. On the left, we have X and Y. On the right, we have NER. And these are models that are trained. So each dot is a different model. And these models are first trained all on 125,000 update steps. That means the models have seen less examples per language. And we can see that for the shared model, the performance drops again, meaning that the more languages the model is actually trained on, the worse the performance gets. However, the modular model maintains performance and one could even argue slightly improves. And this is quite surprising because, again, like the model has actually seen less examples per language, and the modular model still maintains performance. Now, if we fix the number of examples per language, so that means all models have seen the same number of examples per language, we still see the same pattern for the shared model. So the more languages we train on, the worse the performance gets. And in fact, the modular model improves. So we would have been happy if, you know, the performance would have maintained because the model does not actually see more examples for the individual languages, but instead it actually improves. So not only does modularity mitigate catastrophic interference, it actually results in positive influence between languages where the performance actually improves, which is quite surprising. Okay, so the final question that we ask ourselves, and I'm gonna skip this mostly, is whether or not it's important to pre-train on a language. So the question was, do we have to fine-tune all the weights on each of the target languages, or can we just add it later on? And we have like this complicated setup where we have one model and which is where the language is missing and so on. And we have a complicated setup where we split based on language family and script and so on. All of that is not that important because it turns out that if you train on a diverse set of languages, it doesn't matter. You can add languages later on, which is very important and quite interesting. That is not necessary for us to pre-train on all the languages, but we can add languages later without a drop in performance, at least for XNLI. Okay, so in future directions, models are getting deeper and deeper, sparser and sparser. There's catastrophic interference between modalities. By adding modularity during pre-training, we hopefully can mitigate that while being prepared to be modular, and we can add new modular components further down the line, which hopefully helps us to compose these different modular components and help us in this general direction. But there's so many future research questions like, what's the best architecture? Do we do deterministic routing or mixture of experts type of routing? How do we evaluate modularity? How do we compose? As we've mentioned, like adapter fusion is not the best way. So in general, adapters are parameter efficient, modular, and composable, and they are applicable to out-of-distribution generalization scenarios such as cross-lingual transfer, and they mitigate catastrophic interference. So thank you very much for listening, and I'm very happy to take more questions, but we're, I guess, over time a bit.
Thank you so much, Jonas, for the great talk. I will now open the floor for any last-minute questions that the audience might have. You can either ask the question directly or you can post it on the chat and we will ask it on your behalf.
So just training time is a question that I wasn't sure had been addressed. I think if you have adapters, especially in the bottleneck form or additive layer, you still have to do full back propagation, right? I wondered if any of the variants that you spoke of at the beginning in at least part address this, and if you see a way out, because it seems like, you know, unless we really have those big GPUs, we're still kind of hosed.
Yeah. So it turns out that adapters are actually faster to train, just because you don't have to backprop. Well, you have to backprop through the entire model, but you don't have to calculate the gradients for all weights directly. You just need the grades with respect to the activations, and so all the frozen layers weights are like you don't need any gradients for those at all. So that is a bit more efficient. It turns out 40% more efficient than if you would fully fine-tune the model. We have a paper called Adapter Drop, where we benchmark all of that and have a huge appendix on all the statistics around that, how much faster they are. But it is true that we basically have to backprop until the first adapter appears. And in the same paper, we also evaluate what happens if we only have adapters in the later layers. And depending, so basically that means that you don't have to backprop until into the earlier layers, which is again more efficient. And depending on the task that we're interested in, the performance, is somewhat the same. So more semantic tasks, if I can call them that, like NLI, they tend to perform equally well if we only have adapters in the later layers. But more linguistic tasks such as COLA, they perform terribly if you don't have adapters in the first layer.
I see Ulf raised his hand.
Yeah.
Feel free to ask.
Sehr interessanter Vortrag. Dankeschön, Jonas. I have a question regarding foreign language transfer. So you made a point that, of course, it helps if you have seen languages. It helps if you have seen scripts before. Did you also investigate with respect to morphological complexity? So if you have a language like English, with relatively simple morphology, even though it might be unseen, it might be much simpler than something that's morphologically rich. And then the second part of my question is, so the NER, named entity recognition task, is a little bit easier on morphological complexity as a task compared to some other tasks. Can you maybe address how much that of a difference that might make?
Yeah, so we didn't really look at the morphologic aspects of the respective languages, but we did see that languages that are closer to each other in terms of language families tend to perform transfer a lot better. So Chinese versus English. I mean, I guess that's not very surprising that if you, I think one language that is part of Sino-Tibetan language families, Mindong, which is very closely related to Chinese. So if you start with by training your task adapter on a Chinese data set, then that performs very, very well if you transfer to that language. So I don't think we've looked into the morphological aspects of the respective languages, but more on the language family aspects. Your second question was regarding NER versus other tasks. So the problem is that as the more low resource language, the more low resource in terms of language we go, the less the less evaluation benchmarks we have available, which is definitely a problem. And in terms of the tokenizer, like if the script is completely unseen, we have even less data available. So NER was kind of the only language that we were able to evaluate on for those languages. And the higher resource languages tend to not require adapters because they're usually already integrated in the model during pre-training. So that's why we have limited information about all of that, because at least when we wrote these papers, there weren't that many evaluation benchmarks out yet, which is changing right now. And I would assume that your you're implying is true, that morphological aspects play a significant role in the transfer performance.
I have one quick question. Do you think that adapters are more beneficial for task or for language transfer? And are there any future studies planned for studying the benefits of using adapters for cross-lingual, cross-task, like something in between cross-lingual and cross-task?
Yeah, so I think that that language is, so I think that it really depends on the scenario that you're interested in. If it's parameter efficiency, then adapters are always an important aspect of that. If it's simply just cross-lingual transfer, then adding modularity on the language level is more important, because your end goal is to perform well on one specific task, and you're not interested if it actually forgets previously learned information. So you're basically ending up with that specific task, and so it doesn't have to be modular anymore when that is kind of the final objective that you have. But for languages, they are you need to integrate this multilingual information into the model earlier on, and they're adding modularity, and then they're not really adapters anymore, because they're already a part of pre-training. So that's why I make this distinction between like adapters and modular components. While from an architecture perspective, they are somewhat the same. They're not really adapting the model anymore. I'm 100% convinced that you need modularity on the language level, because there is going to be a lot of catastrophic interference between all the languages, and it's just very, very efficient to give each individual language more capacity to learn its idiosyncratic information. If you would have infinite amount of compute and infinite amount of GPU space, then maybe that's possible, but it's just like we find that it's just very inefficient to, or much more efficient from that matter, to add modularity or for each language. And this kind of interpretable nature of, which modular component is dedicated to the respective languages is very nice to utilize, especially in this cross-lingual transfer scenario. But yeah, like you can just fine-tune all the weights and the performance is actually better. Like if you compare our latest paper to MADX, we give the model more capacity to learn the task, meaning that we fine-tune all the weights that are shared instead of just adding task adapters. The performance improves quite significantly.
Cool, thank you so much. We will take one last question by Pushde. Go ahead.
Yeah, thank you so much for the great and informative talk. I had a question, sort of a follow-up to what John asked about the efficiency. So in my experience, often I understand how backprop and the degree that you need to calculate gradients might be more efficient, but sometimes, actually not sometimes, almost always in my experiments, while the gradient calculation is more efficient and so each step is faster, the adapter needs more steps to converge. And it often leads to that the overall training times are a bit longer than full fine-tuning. So I just wanted to ask if you have any comments on that, and you think in your experiments, if by changing anything, you could mitigate that.
Yeah, so I'm not sure what type of tasks you've been working on. In my experience, this training longer is especially a problem for smaller data sets, whereas larger data sets don't tend to have that problem. And if you think about it, it kind of makes sense, because once you already have parameters that are specialized for, you know, a language modeling objective, and the learning rate is also significantly smaller if you just fully fine-tune the model. Now here you have randomly initialized weights that have nothing to do with, you know, the task that you're interested in, and so it kind of needs some warm-up to actually identify like how the transformations need to look like so that the task can be solved. And again, like, this is my experience that only very low resource tasks, or not very low resource, but like if you only have a few thousand examples, then you do need to train longer. But if you train on MNLI, for example, I don't think there's a big difference between adapter training and full model fine-tuning. And that, I mean, if like I can see the argument like that this technically is a problem, but if you already have a low resource task, then training that task is quite quick, right? So it doesn't really matter if you have to train for one epoch or more, then because training in general just takes like half an hour or an hour or something like that. And I would say that it would be a bigger problem if during pre-training this would take longer, because that would be days or months or something like that.
Mm-hmm.
And so I don't know, like I would consider that actually inference is more inefficient, bigger problem than that you have to train a bit longer. Because yeah, if you add more modular components, which requires more float point operations, which increases the latency during inference, I would say that is a bigger problem of adapters than yeah, this inefficiency during training. And there are options to mitigate that. So for example, LoRa does not increase the latency during inference. So those are options that one can actually already look into.
Got it. Thank you so much. That was really helpful.
All right. Thank you all for staying longer, and I'm sure the audience learned a lot from the talk and from the follow-up discussions. If you have any more questions, feel free to reach out to Jonas offline. Also personally looking forward to the one-to-one session with Jonas. And yeah, so that's all for today. And yeah, so see you in next NL seminar, which will be next week, and we will have Woody from UCSD, who will talk about interactive explainability in NLP. Thank you so much, everyone.
Bye-bye.
Bye. Peter, can you stop the recording?